Let's see. Okay, great. Hello, everyone. So welcome to our weekly seminar again. So tonight, it's our great pleasure to have Professor Su Weijie from Wharton School of Business and Department of Statistics. So Weijie is a well-known researcher, young and well-known researcher, and a rising star in statistics and machine learning. And he graduated from Stanford, like many of us, and in 2016 with Candace. So Weijie, you got your bachelor from Peking University, right?
Yes.
Okay, good. So many people in the audience also graduate from Peking University, math department. Yeah, good. So Weijie has published many excellent papers and won many awards, including NSF Career Award and the Snow Fellow. So this is which is a very prestigious award for young researchers. So okay, so it's our great pleasure to have you, and so let's welcome Professor Su, and Weijie, please start your presentation. Thank you.
Yeah. Thanks, Professor Lee, for inviting me to give this talk, and also thank for the very warm introduction, and also thank everybody for staying with me. And today I'm going to introduce a concept called Gaussian differential privacy. So it will be a little bit theoretical, but the implication is entirely practical. So this is something that we believe that people can put in action, in practice, if you care about private data analysis. And so I think there's no need for me to motivate the importance of privacy. So nowadays, many of our data contains privacy, and they are analyzed by many agents, by big companies, by governments. And so in this sense, we are living in a world without much privacy compare with our compare with all the days. So so then how can we preserve privacy? So there are many intuitive or ad hoc approaches already, many, and we can list them. For example, can we just remove your name to anonymize your name from the dataset? So in general, this is it's not safe to protect privacy by only removing your names. So there's an example. So this is the Netflix competition. So each author rates a movie from 1 to 5, but the names are removed, so there's no name. But however, in the real world, the same individual can appear in multiple data sets. Okay? You are not only appearing in one data set, you are present in multiple places. So by relating the same individuals across different data sets, so it's still possible to identify some individual. So as a result, the Netflix competition was canceled in second time. And so another way to protect privacy is especially when you deal with a big data set, is to only release the, let's say, summary statistic. For example, you have a data set. I ask what's the average salary of the people in the data set. So in general, this is also not private. For example, there's a paper published a while ago saying that if you release the minor area frequencies of individuals in a data set, so it's still possible to decide whether some specific individual is in or not. For example, if the data set consists of patients of diabetes, so if we can decide that you are in the data set, then we can say that you got diabetes, right? So this is something private. We don't want other people to know this kind of information. And so looks like we have to give privacy, and however, privacy is really important, even from social perspective. So there's some experts on the American Constitution saying that privacy is an American constitutional liberty right. So this means that we need to try our best to preserve privacy. And so there are already lots of efforts. For example, for computer scientists, more than 1 decade ago introduced differential privacy. This is our topic today, differential privacy. So what's differential privacy? Now in retrospect, we know that differential privacy actually has a root in statistics, in particular in hypothesis testing. So, but this connection was only related by Larry Weissman and Henshu Zhou about 4 years later when this differential privacy was introduced. Now let me formulate, let me make the connection between differential privacy and the hypothesis testing more concrete. And this is also our way to introduce the concept of differential privacy. And so this is a typical data set. And so you have many rows. Each row corresponds to an individual, Alice, Bob, Charlie. And each column represents some features. And some features are not that private. Yeah, you can, yeah, for most people, it's okay to let other people know what's your gender, right? And the age, mostly okay. But salary, perhaps it's not, right? Salary is some feature you want to protect privacy. So a typical example of a mechanism or algorithm in differential privacy takes this form. So some people ask you what's the average salary of people in the data set. However, what you release by a mechanism is not the literal average salary. Instead, what you release is the average salary plus some noise. And so this is the most typical example of a private mechanism in differential privacy. So the idea is that you want to add a noise, and this noise can kill or try to hide any individual level information in the average salary. So by adding noise, then, for example, Alice information is gone. But however, you don't want to add too much noise in the sense that you still want to keep the population level information. So you want to kill the individual level information, but still preserve population level information. So this is I think this is the essence of differential privacy. So now let's make a connection between hypothesis testing and the differential privacy. So in differential privacy, we always think that there are 2 words. This is the word S. In this data set, it's going to be Alice, Bob, Charlie, Dave. But there's another reality. Yeah, maybe we can think of counterfactual, right? Not counterfactual. It's really counterfactual reasoning is really hot in causal inference. Yeah, I think there's a high-level connection. So in this counterfactual reality, so it's going to be Annie, Bob, Charlie, Dave. So you see S and S prime, they are almost the same, except for Alice and Annie. So then we have 2 hypotheses. Under the null, we say the true data set is S. On the alternative is S prime. So essentially, the null is saying that Alice is in the data set, or Annie is in the data set. So intuitively speaking, if it's really difficult to perform hypothesis testing, by difficult, I mean it's really hard to tear apart H0 and H1. So in this case, privacy is preserved, right? So it's really hard to tell Alice or Annie in the data set. If it's really easy to do the hypothesis testing problem, then there's not much privacy. So this is essentially the idea underlying differential privacy. And but when you want to do hypothesis testing, you must leverage some information, right? What kind of information you can be based on to do the hypothesis testing? It's the output of the mechanism. So it's kind of this thing, right? So you can observe this value, the noisy average salary, and then you can do the hypothesis testing. So now differential privacy is really hot, and I mean, it's really applied in many tech companies like Google, Apple, and Microsoft. And last year there was a US census survey in each 10 years, every 10 years. So they use differential privacy in many of their statistics. And so the 4 authors also got recognition. So so far, our talk is still about the backgrounds of differential privacy. And so now let's try to talk something new. And so And so this talk is based on these papers, and they are all available on my website or Google Scholar. And in particular, our main focus is on the first paper. So the first paper is the foundational paper for Gaussian differential privacy, so which is also the title, kind of the title of the talk. So this is a joint work based on two author collaborators, Jinshuo Dong and Aaron Ross. Aaron is a CS colleague at Penn, and Jinshuo was a former student, and now he's doing a postdoc with at University of Northwestern University and University of Chicago. So Jinshuo is really a wonderful, brilliant student, and he's a rising star in the differential privacy research. So here we want to contrast two differential privacy definitions. So first of all, they are all differential privacy definitions based on hypothesis testing. And our is called F differential privacy, but the other one is called epsilon delta DP, given by Cynthia Dwork et al. So the first is their similarity. They are both interpreting privacy by hypothesis testing. They're same. So they share the same, they share the same father or mother. So, but next they are brothers, but they are different, right? They are brothers, but still they are different. And in our F differential privacy, we are using the type 1, type 2 errors trade-off in arising from hypothesis testing as a measure of privacy. And but they are using the worst case likelihood ratio. So epsilon delta, the two parameters are basically measuring the worst case likelihood ratio, and how I will discover, I will comment later. And the next, so the privacy measure is given by a trade-off between type 1 type 2 error, right? So type 1 error is always between 0 and 1, and the type 2 error is also between 0 and 1. So this essentially gives rise to a functional parameter mapping the 0-1 interval to the 0 interval. And in epsilon delta, they use epsilon and the delta to describe the worst case likelihood ratio. So the typical way to treat privacy in our framework is to add Gaussian noise, and but in their case, to add Laplace noise. So now let's, before going into the details of FDP, now let's try to first have a very early preview of FDP, essentially to get some intuitive impression of why FDP is something good for differential privacy. So roughly speaking, we are in the remainder of this talk, we are checking 3 criterions. And so namely whether it's informative or not, and how does this handle composition, the last subsampling. So there are many rows, and each row corresponds to a epsilon delta differential privacy definition. So there are many. So we want to convince you that our FDP is doing well across the 3 criteria. So what informativeness? So roughly speaking, you want to make sure that your privacy parameter, so for example, epsilon delta, really characterize how private the mechanism is. However, in epsilon delta, the 2 parameters are really too coarse, not enough to describe complex things like privacy guarantee. So this is like if you want to squeeze a square into a circle, right? Circle has is non-linear, but square is a piecewise linear thing. So you have to lose something. So similarly, if you are dealing with Rayleigh divergence, and it's still not enough to describe the complete privacy information. And the more intuitive is the composition. So composition is very natural for each privacy definition. So because in our real world, a data set is used always millions of times, right? We always use like ImageNet for millions or billions of times, the same data set. So you ask the same question about the same data set. As you ask more and more questions, you get better understanding of what's going on in the data set. So the privacy of the data set is declining. So composition is concerned with how does privacy degrade as you ask more questions. So short answer for epsilon delta is that the computation theorem for epsilon delta is not sharp. It's not good enough for practical use. So subsampling is also well used, and because for many algorithms, you only need to, for example, subsample 10% or maybe 50% of your data set, and you can only focus on your subsample in analysis. So this is, for example, the case in deep learning training. So each time we subsample a mini batch size, right? Maybe 32, 128. So you only do compute the gradient on the subsampled data set. And the equation for each differential privacy definition is how does privacy amplify? Because you only sub 10% of the points there. So by definition, intuitively speaking, you amplify privacy, right? Because most of the times, an individual, for example, me, is not included in the subsample. So my information simply will not influence the outcome. So my privacy is perfect in this sense. Yeah. So now let's formally introduce F differential privacy. So let's go back to the hypothesis testing interpretation of differential privacy. You have null and alternative. By the way, here null and alternative are symmetric. Typically in statistics, null and alternative are not symmetric. Null is it's different. But in the hypothesis testing in differential privacy world, the null and alternative are entirely symmetric. And now let's define the type 1, type 2 error. And it's very simple. And what's type 1 error? Type 1 error is that so you are the reality is null, but you are rejected, falsely rejected. This is type 1 error. So it's like you are healthy, but you are tested positive. So this is type 1 error. So what is type 2 error? Type 2 error is that the reality is Q, is an alternative, but mistakenly you accept the null. So this is a type 2 error. So it's like you are sick, you got COVID-19, but you are tested negative. So this is a type 2 error, right? So this is some errors, in our real life. So, and now let's define the so-called trade-off function between two distributions, P and Q. By the way, P, Q denotes the probability distribution of the released outcome by the mechanism N. For example, what's the distribution of the noisy average salary? So this is P for the Q, depending on the reality. And so this is the minimum for any alpha between 0 and 1. So the trade-off function at alpha is the minimum type 2 error. Is the best rejection rule phi you can find, such that the type 2 error is below the specified alpha. And then what's the type 2 error? So this is the best hypothesis testing you can get at alpha. And so this is from stats 101. We know that this is given by the Neyman Pearson lemma, right? You can consider the likelihood ratio between null and alternative, and then you can set certain threshold cutoff to do to find the type 2 error by setting the type 1 error equal to alpha. So any questions about this definition? So this is the main the core stuff of this talk.
Is phi is a probability of certainty?
Say again, sorry, I didn't catch that. Phi.
The rejection rule phi is fixed or not fixed?
Good question. In general, phi can be randomized. This is because, for example, if the outcome is some discrete integer value, right? The outcome is counted, for example, 1, 2, 3, and then in order to really set the type 1 error equal to alpha, you have to do randomization. Yeah.
Okay, I see.
Yeah, good. So now let's come, this gives us the definition of F differential privacy. So any algorithm or mechanism is said to be F differential private if the trade-off function of two neighboring data sets, and S prime is always larger than or equal to the parameter f. And so this is in the pointwise sense. For any alpha, the inequality should hold for any alpha between 0 and 1. So this is saying that if S and S prime, so by neighboring, we know that S and S prime, they are very similar. They only differ by one individual, say Alice or Annie. And then based on the outcome, the trade-off function is by testing, if you want to distinguish between Alice and Annie, and then you will always incur a type 2 error larger than or equal to the type 2 error given by f for any level alpha, no matter if you want to, for example, set alpha to be 5%, 10%, and the type 2 error you incur if you want to deal with Alice and Annie, it's always larger than the parameter f. So this is the interpretation. And for example, if f is a trade-off function given by p and q, okay, then we can say that the privacy of Alice and Annie is at least as good as the privacy between p and q. So if p and q are two probability distributions overlap a lot in their space, overlap a lot, so then there's really no much way to distinguish between them, right? So they are really similar. But if p and q are very different from each other, right? And for example, p is typically, a value from p is typically about 100, but from q, the typical value is 50. So 50 is 100, right? So they are far apart. So it's easy to tell which one you are from, whether p and q. So in this case, there's not much privacy. Got a question? May I ask that T is a total variation distance? No, T has nothing to do with total variation. T is the trade-off function. It's a function mapping 0-1 interval to 0-1 interval. For n alpha, what's the type 2 error? So this is a trade-off function. So in statistics, you can set any alpha level, right? You often say, oh, the significance level of the test is 5%. So this means that if you are healthy, and then with at most 5%, you will be tested positive. So this is type 1 error, right? So type 1 error, 就是假阳性. And so type 2 error is that then usually fix the type 1 error. People want to minimize the type 2 error, right? Meaning that if you are really sick, you are contrasted COVID-19, and what's the minimum error that you are tested negative? So this is 假阳性, right? And so this is the trade-off. Normally, if you alpha is larger, beta is larger, right? So there's no way to make both alpha and the beta small. Yeah, thanks for question. And so now let's briefly talk about how the relation between epsilon delta and our FDP. So long story short, actually epsilon delta is a special case of our FDP. And so recall that the definition of epsilon delta actually takes this form, a little bit complex, right? But roughly speaking, if data is very small, so basically this is saying the likelihood ratio between S and S prime is at most E to epsilon. Okay, so epsilon basically can be thought of as the largest log likelihood ratio. So E is any event, okay, any measurable event. So our story actually translates a result due to Larry Weissman and Henshu more than 10 years ago. So it's saying that epsilon delta dp is also FDP, and what's the corresponding trade-off function? Take this form. Yeah. So here the intercept delta. So here at this point is 1 minus delta, and then you draw a line, straight line. So like this, everything is matched with respect to the 45-degree line. So the symmetry comes from the symmetry between H0 and H1. So But however, so this is actually our motivation for our project, because we see why you should use 4 segments, right, to describe a trade-off function. The trade-off function can be any 0, 1 interval, right, between y. So to ad hoc. Also with probability data, here the likelihood ratio is infinity. So the arbitrary bad thing can happen here. So this is also something we want to overcome. So so there's a more profound connection between FDP and the epsilon delta. So epsilon delta actually can be described by multiple pairs and epsilon and the delta. So this is actually a main drawback of epsilon delta. This is because you have an epsilon delta parameter, but you can make epsilon slightly larger and make delta smaller. So there's always a trade-off. So this actually causes some issue, right? Because if you want to stick with epsilon delta, you have multiple pairs of epsilon delta to describe the same algorithm for privacy. But then the question comes down to this: which pair of epsilon delta do you want, right? So there's some non-uniqueness there. So intuitively speaking, if under certain measure, there's some uniqueness for the parameter. So there's some issue with the definition. So we can have multiple, but actually what our F differential privacy does is just take the upper envelope. So you have many epsilon delta, right? And the maximum of this envelope is just our F, the FDP. And then we can do the reverse thing. So given you have an FDP guarantee, and you can also translate it to epsilon delta. How? So basically you fix data is here, the length here is data, then you draw a tangent line. So then tangent, everything is symmetric here. So you get many pairs, and then you recover epsilon delta. So essentially, epsilon delta, the drawback of epsilon delta lies in its non-uniqueness, but FDP overcomes this difficulty by using a functional parameter to encode all the information of these epsilon delta pairs. So now let's introduce a subfamily of FDP. And so this is going to be the title. It's the title of the talk, Gaussian differential privacy. So here, the 2 probability distributions, let's record this, it's going to P and Q, right? Here, this is P, this is Q. They are both normal distributions and with only mean shift. So intuitively speaking, if mu is really large, for example, mu is larger than 3 or 4, we know 3 sigma principle whatsoever, then the 2 probability distributions don't overlap much. They are very far away from each other. So there's no much privacy. If mu is small, say mu is smaller than 1, then they overlap a lot, right? So in this case, there's lots of privacy. So this is the closed form expression. So we see an mechanism is mu GDP if the trade-off function between 2 neighboring data sets is always larger than G mu. Okay, G mu is here. So this is single family prime definition, and roughly speaking, we F in general can be kind of non-parametric, right? Okay. But here we are parameterize F using only mu. So what's more important is a central limit theorem, and we will see in a minute. So there are some plots of the G mu function, and if mu is small, you see it's quite close to the 45-degree line. Here, this is perfect privacy. Here in this line, you know that's the type 1 error and the type 2 error sum to 1. So it's just a toss a random coin. In this case, the 假阳性 and 假阴性加起来等于1，是吧? In this case, this is the worst case we can do for hypothesis testing, right? Worst case. So this means that you simply cannot distinguish between H0 and H1. So this is perfect privacy. So if you are slightly below, you really sacrifice a tiny bit of privacy, but most of the time you are still safe. but here G mu is 3, then it's dangerous, right? Dangerous. So in this case, that's good way to break your privacy. So the typical way to achieve privacy in our FDP, especially the Gaussian DP, is to add Gaussian noise. So roughly speaking, you are the you are the user, and there's some data set with some curator, and you can make a query, ask what's the average salary, what's the average whatever, the average weight of the people in your data set, and then the curator release the information by first compute the true statistic. This is a true statistic, and then plus some noise, And but the question comes down to how much noise do you add, and what kind of distribution of the noise you should add, right? So this highly depends on the so-called sensitivity. Sensitivity is basically the largest perturbation of the statistic of two neighboring data sets and S prime. Okay, so in the case that if theta denotes the average salary of people in the data set, so this is basically the largest salary of the person, right? So if there's some really rich person in your target, in your radar, then the sensitivity can be very large, right? If, for example, Bill Gates is there, then this is can be very large. But if most people are about the same, then in terms of salary or net or wealth, then this is going to be small. So so the short answer is that how much noise do you add? You add Gaussian noise, and the sigma here is given by this identity. If sensitivity is large, then you need to add more noise. Okay, if Bill Gates is there, then you need to add much noise. Otherwise, you kind of small. It also depends on the mu. How much noise do you, how much privacy do you need? If mu is small, then you need to add more noise because you are a very cautious person. If mu is large, then you are very relaxed, right? So you can add less noise. So maybe in terms, maybe let me skip this part because this, let me go to the to save time. I will also go through this part a little bit quick because this part is very theoretical. So the short answer is that there's a theorem due to Blackwell saying that so the trade-off function actually records all the necessary information you need between in hypothesis testing, so P and Q. So the answer is that if you have the hypothesis test, if you have the trade-off function F, you can just throw away your P and Q. That's it. You can just study F. So F is the complete information. It's like in statistics called sufficient statistic. But this is not the case for other differential privacy definition. For example, the Renyi divergence. So Renyi divergence, define for any P and Q, use this Renyi divergence. If gamma is 1, this is reduced to KL divergence. And so the short answer is that so I will not elaborate this proposition because a little bit theoretical, but the main message is that Renyi divergence is not informative. It loses some information. Yeah, now let's go to the most, I think, perhaps most significant part of this talk. So about composition. So composition is about some adversary ask multiple questions and in the hope that you will have less and less privacy. So for example, if you ask how many patients, right, and sometime, and then ask the same question again later, and by contrast the number you receive, so you can determine that this lady has diabetes. So the question is how much privacy, how does privacy degrade, compromise on the composition, right? You ask more and more questions. So first, let's set up the notation for our discussion. So M1 is our first question. Hey, what's the average salary, M1? And M2 is the second question. Hey, what's the average, I don't know. What's the average IQ of the people in the data set, right? Yeah, you can ask many questions. And so the composition is just the combination of everything you have. Okay, you can put the first coordinate is M1, second coordinate is M2. You can combine them. So as you ask more and more questions, you have a increasing vector, right? Increasing vector, and so you get more information about the data set. So here, M2, the question you ask in the second round can depend on the outcome of your first question. So there's adaptivity there. And so in general, you can do composition for arbitrary number and arbitrary number of algorithms. So now let's define the so-called trade-off function, tensor product of two trade-off functions. So the trade-off function f given by p and q, and another trade-off function given by p prime, q prime. So you can define the trade-off function. They are tensor product. So the tensor product is still a trade-off function, but it's a trade-off function between two product measures. So p times p prime, q times q prime. So if the reality is Alice is in the data set, then the first, this component has distribution P1, right? P. And the second coordinate has distribution P prime. So the overall distribution, the product distribution is P times P prime. If the reality is any, then it's going to be Q times Q prime. So this essentially explains the idea, why we use this definition. So the good thing is that this is cumulative and associative. And so you can ignore the order when you do multiple tensor products, for example, tensor product of three trade-off function. And in the case, if you are doing trade-off tensor product for Gaussian mu GDP, and then the resulting mu is just the L2 norm of all the previous terms you see. And so there's a kind of an algebraic flavored theorem. So saying that if each mechanism Mi is Fi differential private, then their overall combination is also FDP, and the corresponding F, the trade-off function, is given by the tensor product of all the small p's Fi, F1 tensor product up to Fk. So this is your trade-off function. So this is in general, it's the sharpest you can get if there's no additional information provided. And so yeah, this is our theorem. And but this theorem is not that it's only conceptually useful. Conceptually, I mean that this is essentially saying that FDP is closed, right? On the computation operations, you can always stay in the FDP world. You do not need to worry about when FDP definition is not sufficient for your current algorithm. But this is not useful in the sense that what this guy, right? What this thing, how can we compute? So I can tell you that in general, the computation of such tensor products can be very complex if k is increasing. So, but the good thing is that we have an approximation tool called using central limit theorem. So the short answer is as follows. So this theorem is really is blatantly informal, because to formally state this theorem, we need to, for example, need 2 slides to prepare the notations. And but you are welcome to look at our papers for the full theorem. So to informally state this theorem, saying that you have an increasing triangular array, and so k is increasing, and then for each fki is very close to perfect piece of information. You only release a tiny bit of privacy, not too much. But then their overall privacy, which is given by the combination, will converge to a Gaussian distribution, Gaussian differential privacy. Here essentially depends on the first and the second moments of all the small pieces of trade-off function, and this convergence is also uniform. So this theorem does not look like any typical central limit theorem, right? But I can show you that the proof is entirely the same as the central limit theorem. So because essentially the proof this expression using the log-likelihood ratio, and you can use the Neyman-Pearson lemma to select the cutoff to do the hypothesis testing problem. And so this is essentially an effective approximation tool. As we said, this theorem is useful. It's only conceptually useful, but practically it's nothing, right? How can you compute? But now we have a computation tool using central limit theorem. And you may be asking, so this theorem is saying that it's only valid if k is large. But the good thing is that in our real world, many algorithms, many machine learning algorithms actually can be decomposed to many steps, a large number of steps of small pieces of operations, like training deep learning, right? Each time you do a back propagation, and you will do millions or billions of back propagations. So k here is very, 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 very large. So this is a final sample guarantee. So let me skip this. So essentially, let me say a tiny bit on this comment. So if you really want to compute the exact value of this trade-off function, exact, then this is gonna be Sharpe complete. So what's Sharpe complete? I only can tell you that it's more complex than NP complete. So that's it. So yeah, let me skip this part. So now let's consider how useful this approximation is for a typical problem. And here actually k is only 10, it's very small. And so the exact composition actually we can still compute because k is small, and it's given by this red line. And our approximation is given by the blue line. So you see the blue line and the red line overlap a lot, right? They basically coincide with each other. So they are almost the same. So it means composite approximation is good. In contrast, if you are using delta, for example, delta is 0.01. So the trade-off function is given by this dashed line. So there's a region, right? The middle ground. The middle ground is what you lose if you use epsilon delta. And so here there's also a universality of central limit theorem. So in this case, you do not do computation, but instead you are considering a query answering with high dimension. So theta of S can be high dimension. So recall that you can ask, what's your average salary? What's the average IQ? What's the average weight? Many, many questions, right? You can do a sequential. So this is computation. But what you can also do is to ask all the questions at the same time, right? At the same time, there's no adaptivity here. So in this case, if you add the noise to your high dimensional query, so in most general case, it's also going to be Gaussian differential probability. And moreover, you can have a kind of uncertainty principle here. So the noise variance, so how much noise do you need to add times how much privacy you need to ensure, is always larger than lower bounded by the dimension. So the dimension, what's the dimension of this statistic query answering? So essentially how many questions you ask about like IQ, weight, salary, whatever, is characterized the fundamental difficulty for protecting privacy. Okay. So now let's go to the last part, and so briefly talk about subsampling. So subsampling, let's maybe just go to this part. So subsampling, for example, you can always use the example of mini-batch in deep learning training. So M is the mini-batch size, for example, 128. So each time you select a 128 size subset from your data set, and P is a small number, right? M over N, the subsampling ratio. N is the total number of data points, images in your data set. So there's such operation. FP is this, defines this. So with probability P, I'm selected in this subsample. Okay, so my privacy cost is F. But with probability 1 minus P, I'm not selected. So my privacy is perfect. So this is a kind of weight convex average. And since everything is symmetric, you need to also consider the inverse function. And you consider the mean because you want to protect privacy for both cases. But however, in this case, it's not going to be convex. You need to double conjugate in order to make it convex again. So this our theorem is as follows: if the original mechanism N is FDP, then after subsampling, it's going to be this FDP. So by applying this operator on your original trade-off function, this is also tight. Okay, so everything now you see it's reduced to some operator. Okay, operator. This operator maybe does not look still look complex, right? But what I want to say that now everything is reduced to math, right? It's very mathematical. So this makes the analysis and this will facilitate the analysis as well as, for example, developing new methods, because this is very and easy for mathematical operation. So this is our gain, and so in the original earlier in the literature, so this is the original FDP, epsilon delta DP guarantee, and now you use subsampling. Subsampling ratio is 20%. Okay, so in the literature, people say, okay, the resulting privacy is given by this blue line. But what our subsampling theorem tells us that is the real privacy guarantee is this. Okay, real this. So you see, we gain this region. This is a region we gain by using our subsampling theorem for FDP. So hopefully I have convinced you that FDP is doing well in these three criterions. And now let's go to its application. So this is joint work with my student Zhiqi and the Sam Jingshu is still here, and the Qilo and colleague at Penn. And so privacy concern is enormous in deep learning, right? Because deep learning is used for our face recognition, almost many high-stake decisions. So privacy is often violated. So there are millions of such examples. So now there's a really, really important urgent question for many companies like Google and Apple. They are really trying to develop private deep learning, incorporating differential privacy in their many products whenever deep learning is used. So this is especially the case because early this year, Apple updated its privacy policy on iOS 14. So iOS 14 now imposes very strict privacy regulations. So this makes the life of Google and especially Facebook very difficult as far as I know. So they are trying to use they have to use differential privacy for their products. But the question, of course, if you use differential privacy, you will lose utility, right? Because you add noise. And the question is that what's the minimum amount of utility you have to use? So we always want to lose less. We are still happy if you lose, for example, 2 or 3 points in prediction accuracy, but you will not be happy if you are losing maybe 10%, right? So this is private deep learning. And so short answer is, let me briefly summarize. So you do 2 operations on top of the original training in deep learning. So you do gradient clipping. So you basically, if the gradient is too large, you project it to the radius of R. You still keep the same direction, but now you reduce the radius. And the second is at Gaussian noise. So this is the average gradient. So the gradient computed from your mini batch, and then you add a noise to it. So then you update your gradient. So you can also do the same thing for Adam. So it's very similar. So now let's use our FDP to do the privacy analysis for deep learning. So you know, deep learning is basically this equation. You first do subsampling from get a mini batch, and then you compute the noisy gradient, okay? And you repeat this for t, for example, 1 millionth of times. So this is basically subsampling plus composition. And then let's apply our theorem for the subsampling and also the theorem for composition using central limit theorem. We can immediately get this simple formula guarantee. So this is asymptotically mu GDP, and the mu is given by this equation identity. Okay, so yeah, very simple, right? The sigma is the noise. So now let's consider some experiments. So this is yeah, very simple example, training on MNIST. And if you want, when you achieve 95% accuracy, in this case, how much privacy is left? In using our our FTP, and we are saying that the privacy guarantee is given by this red curve as the trade-off function. But using the moment content technique given by previously by Google, so the privacy is guaranteed here. So the difference is more dramatic when you achieve private accuracy 96.6%. So the difference is it becomes more significant. Our privacy is still good, but the moment content by Google Brain looks bad, pretty bad. Here, both type 1, type 2 error can be more than 5%. Yeah, there's no much privacy left. So this is a even more sharp distinction between our two approaches. Yeah. So here you see our FTP saying that the privacy is basically the same as testing standard normal distribution, and the normal distribution with a mean 1.13. So yeah, basically 1 standard deviation, right? 1 standard deviation is still, I mean, there's still reasonable privacy there. But for moments content, it uses epsilon data. So epsilon here is large, 7.1. So recall that e to the 7.1 is more than 1,000. So the likelihood ratio is more than 1,000. So most reasonable people will say there's no privacy, right? It's really easy to tell apart P and Q if the likelihood ratio is more than 1,000. So since you get better privacy, then of course we can leverage the better privacy for better prediction accuracy, right? So you can add less noise. So this is a example, 2 examples saying that we improve over the Google Brain's moment content. And so this is a demonstration, and I hope that we can do more experiments to show that we can get more significant improvement. So here the improvement is real, but you may say that the improvement is still not significant. I agree, but yeah. So this is, I think, for future work. So now let's summarize. And so there's multiple directions, and I think FTP can be used for basically any places where epsilon delta DP is used. So yeah, you can try. And sometimes, yeah, it can give you some benefit, sometimes may not. Yeah, I think everything should be a case-by-case study. So hopefully I have convinced you that FTP is doing well in informativeness and the composition and the subsampling. So last of all, and I would say that FTP achieves the state of art for training differential private deep learning models. So FTP is here, and the epsilon delta and the GDP are special instances of FTP. And by using central limit theorem, everything goes to GDP. Okay, GDP. So these are based on these papers, and yeah, you are welcome to take a look. And we have make it available at TensorFlow to do the privacy analysis for deep learning. And so since here everything is about G, right? Gaussian and Gauss. So this is the return of king. So Gauss makes the becomes the boss again in our differential privacy literature. Yeah, and I'm done. And thank you for staying with me. Yeah. Yeah, thank you. Any questions?
Thank you very much. And let's thank the speaker and before we ask questions. So for the deep learning experiments or other experiments, do you have the plots for divergence-based results?
Yeah, thanks for question. So divergence-based essentially is the moments content here. So moments content was developed by a group of Google researchers in Google Brain. They are using the Renyi divergence. So Renyi divergence was introduced by Ilya Mironov, and a former Google Brain researcher. But recently he moved to Facebook. So they are using. So Ilya introduced a Renyi divergence based differential privacy, but they always finally they always translate it to absolute data. So Renyi divergence, Renyi differential privacy is only a intermediate step. So they are always using absolute data as they are our final for their final product.
I see. So in your plots, the other plots, what's like triangles look like? I mean, yeah, like those plots. So those are the divergence based. Yes.
Yeah. I made divergence based on the Renyi divergence.
Okay. Thank you. Other questions?
Weijie, in your mind, so which definition of differential privacy is more practical? In the sense, can be easily satisfied in practice.
Yeah. Good question. So there are at least two perspectives we can take for evaluating a differential privacy definition. So first of all is about how powerful. How powerful means that fix your privacy budget. So this is a privacy budget, and what's the best performance you can get for your private model. And so here we have actually this talk essentially shows that FDP is doing the best in this criteria, in this perspective, because this always give you the sharpest privacy analysis. Once you have the sharpest privacy analysis, you can always trade privacy for performance. And but another perspective is about interpretation. And so actually, I recently talked to some Facebook people, and so their issue is that when they have some privacy guarantees for their machine learning products, they have to deal with talk to some legal people. So they are lawyers, and but for them, they only they have only learned math up to high school, right? So it's really hard to explain something like a little bit complex like FDP to them. So, but absolute data is perhaps the most difficult thing they can comprehend. And, so in this case, absolute data may have some advantage. I have to admit, absolute data, because they have two parameters and essentially two numbers, right? Two numbers, and so some non-experts on privacy can understand, and so can make some legal people happy, and this is perhaps not the case for FDP, because FDP, the function F is a functional. Yeah, it's too complex to tell what is F to some average people.
Okay, sorry, that probably was not my question. So my question was that I mean, you probably need to design different privacy mechanism, right? Inject different forms of noise into data to satisfy this different definition of differential privacy, right? So
no.
which way?
No. So for any algorithm, any noise you add, whatever, we can always describe using our FDP can describe. Absolute data can also describe. Yeah. So absolute.
Is that difficult to design this the injected noise? I mean, what sort of noise you want to inject into the data to protect the privacy? So is that easy to implement?
So epsilon data, the different privacy definition are two different languages, right? And so, so like English and Chinese, for any things, for any ideas, for any algorithm, we can always use Chinese or English to describe. And yeah, so, but the thing that there's some complexity. Maybe Chinese is more concise in this case, and so maybe this is the case for FTP. I'm not sure I get your question. Yeah, did I?
Okay, yeah, I just don't know how to, design this privacy preserving mechanism.
Oh, yeah. So in general, this is a really, really complex thing. There's no principled way to do it, as far as I know. But there's always a template. For example, you can add Gaussian noise. So in this case, you always preserve privacy. Yeah, you maybe here. Yeah, you always preserve. You get Gaussian differential privacy. Yeah, here. But this is perhaps not the best way you can do, because the analysis of theta usually comes with a pipeline. So there are many intermediate steps. You can add noise in the middle, right? You can also add noise at the last step. So there are many, many ways. You can also add noise at the beginning. So this is called a local differential privacy. And which one is the best is usually it's a case-by-case matter.
Is that widely used, this concept, differential privacy in industry? Or it's just a theoretical concept so far?
Oh, it's really used. For example, our iOS, for example, if you update your iOS if you're using iPhone, and they will say they are using differential privacy for some when they analyze your data. Yeah.
Okay.
And the Google and the Microsoft and are also using.
Okay, thank you.
Yeah, thanks.
So I have a question. Is this like a FDP noise sensitive? Like you add a noise, like a Gaussian noise, is it very sensitive to the sigma square?
Yes, this is really depends on the question you ask. If the sensitivity is large, then you need to add more noise. Otherwise, you can add less noise.
So basically, it's a difference between the S and the S.
Yes, to neighboring S and S prime, they only differ by one individual. Yeah.
Yeah, and I think in your talk, you talk about some other type of noise. Like if it's other type of the noise, like what happened to the FDP?
Oh, yeah. So if you're using different, for example, you had a Laplace noise, then you can essentially consider, so essentially in the definition of FDP, you always start with the P and a Q. So now, for example, P is the Laplace noise, and the Q is the Laplace noise with mean shift 1. Yeah, so you can still define the Chita function. The only thing that perhaps, yeah, you don't have
closed form.
For Laplace noise, we still have closed form expression.
Oh,
but it's not that elegant, I think. I guess it's not as elegant as Gaussian DP, because for Gaussian DP, it's essentially, we know there's a thing called linear discriminant analysis, right? For high dimensional multivariate normal distribution. If you want to distinguish between them, you do projection. And so essentially, yeah, everything comes down to one dimension, right? One dimension. So this is simple for normal distribution, which I'm not sure, which perhaps is not the case for other distributions.
Okay, so that's also why you say the kings come back.
Central limit theorem is everywhere.
Thank you, Professor Su, for the talk. And I want to ask a question about the composition part. So, in the composition, you mentioned that you can represent it as a tensor product. So I was wondering what is the connection between composition and sequential hypothesis testing? Because in sequential hypothesis testing, I'm not sure it can also represent it using tensors because it's not commutative. Right? So I want to hear your opinion.
Yeah, they are. I think they are conceptually very related. Yeah, thanks you for your question. So in sequential hypothesis testing, and so the only perhaps the difference is that in sequential hypothesis testing, you can have different non-alternatives, right? In general. However, in this FDP framework, we still fix the non-alternative. The non-alternative are always fixed. Yes, we do not change. So you just essentially you are repeatedly do the hypothesis testing, but using new data. Yeah. So you are always interested whether it's Alice or Annie. So the same hypothesis, so you can use more information. For example, using their average salary to decide whether it's Alice or Annie, or using their average weight or average whatever. So to decide. Yeah.
Thank you.
Yeah. Thanks.
Oh, okay, I have a question. So other than adding the random noise, is there any other alternative options? Because such as the exponential mechanism, like in the epsilon delta privacy in the FDP, or maybe the mechanism can be a random stochastic algorithm like SGD. So is it possible to extend your theory to things like that? Okay.
Yeah. Thanks for the good question. Yeah. So so essentially this can always because everything comes down to the P and the Q. So in exponential mechanism, so the P and the Q, the outcome is discrete, right? So for example, you choose 3 colors and it's not continuous, but you can still always define the trade-off function. So there's no problem. In principle, then there's no problem. But the issue perhaps will appear in composition, I guess. And because composition, if it's not additive, you are not adding noise. You are using, for example, exponential mechanism. Each time you choose with probability some possibility, right? Yeah. And in this case, the central limit theorem perhaps will become. Oh, I'm not sure. Yes, but perhaps it's hard to get central limit theorem.
Yep. Another question is, can this be combined with stochastic algorithm like SGD? So I think, is it possible to design the FDP based differential preserving SGD methods?
Yes. So we can do, for example, for deep learning. So in deep learning, so although there is some kind of I always say there are subsampling, but subsampling is not exponential mechanism. So each time you subsample, for example, 32 images from ImageNet, right? And you compare their gradient, noise gradient, and you do SGD. So this gives us this privacy analysis. So essentially, deep learning trained by clipping and adding Gaussian noise is mu GDP. Yeah, the mu is given by this form. So T is the number of iterations. Of course, if T is large, then you will incur more privacy loss. Also depends on the subsampling ratio. So N, for example, if the data set is ImageNet, for example, 10 million. If M is small, then you get, this is small, right? It also depends on the noise. If you add really much noise to it, and then this will close to 1, this will be small. If you add small noise, then this will be large. So so everything here is given by this theorem.
Okay, thank you.
Yeah, thanks for your question.
Hello, Wei-Jie. Could you go to the
Right.
part you have G mu 1, G mu 2, G mu n, and
Sure, sure.
right.
Yeah. Yeah.
Oh. What's that part?
I think, yeah, here I think. Yeah. Here, right? Yeah.
It's
So
at G mu 1 plus G mu 2 plus G mu n is the same as G mu. Mu is a Euclidean norm of those mu I.
yeah. So
You have
here,
you have formula somewhere.
yeah. So this is a composition, I think. So the composition of G mu. Mu k.
Sure.
Yeah.
So this reminds me, maybe is correlated or maybe not. So this reminds me, say in random matrix, we usually have like a semicircle law. Have a semicircle G mu 1, semicircle law G mu 2, semicircle law G mu k. Then you do we call the free.
Yeah, free probability theory. Yeah.
Yeah, it's a free convolution. In your case, it's a convolution. Then G mu also carries the semicircle law. So this is like an invariant under convolution. The probability no change much. In this case, G mu 1, G mu 2, G mu k, the same thing, similar thing, but with different metric mu 1, mu 2, mu k. After convolution, you still got a G thing, but with different mu. So maybe you're related, maybe not. Just your stuff, make me think about that way.
Oh yeah. Oh, thank you for making this case, for making this connection. I think I will take a look, and yeah, maybe at a high level they are related. Because the free probability is a kind of very elegant subject. Yeah, if there's connection, it will be really good.
Yeah. Now, another one is, say, you have a central limit theorem. Basically, there's 2-point test. You use Neumann-Pearson lemma. So if you have monotone likelihood ratio, then things, somehow reduce to sum of independent random variables. Now, for this type of thing, there's so-called moderate deviations. Moderate deviations, large deviations, similar to what you got. But anyways, you have a central limit theorem. Central limit theorem, in the central limit theorem, that you could have a dynamic case, means you have another parameter along this normal distribution. So you could have a Brownian motion, for example. So I'm not sure is useful or helpful, in your study. But somehow, I think, once you have central limit theorem, the next thing automatically you think is, you could have Brownian motion, something like that, or Gaussian process, another Gaussian process.
Oh yeah. Interesting. Yeah. Especially large deviation is really important. Yeah, because central theorem more care about the approximation in the bulk, but if you come down to the tail, then large deviation will be very more powerful than central limit theorem.
You may check Amir Dumbo and Oliver Tony. They wrote a book called Large Divisions and Applications.
Oh
so
yeah,
they have a section. The section tells for this type of stuff, the Neumann-Pearson lemma, they have large divisions, moderate divisions, something like that. Yeah.
Oh yeah. Thank you. I will take a look.
Are there more questions?
Oh, I have a question, maybe last question in the chat. It's a good question. Good question. So the question is about the role between alpha and beta in the definition of the trade-off function. So the answer is this: for a fixed and P and Q, they are not symmetric, alpha and beta. But when we really define, comes down to the definition of for FDP, alpha and beta must be symmetric. So F in general can be non-symmetric. So, but we can always make it symmetric and make it also more tight.
Yeah, also you use the Rini divergence. So Rini divergence special case if gamma equal to 1, that's the KL divergence. So KL divergence, we have for any two probability measures, we have a lot of description about somehow distance in between. So I work in the past in like KL. I use a KL divergence, total variation distance, and even this so-called Kontonovich distance. So you have a lot. I'm not sure why you're particularly interested in this Rini divergence. You have a particular reason. I said we have many representative, many possible alternatives, but why you somehow like this Rini divergence so much?
Okay. So good question. And Rini divergence was introduced by Rini differential privacy introduced by Ilya Mironov, and so it's other people's work. And but
you respect them, huh? You respect him.
Yeah, but it's, I think many, for example, total variation norm is not ideal for differential privacy. So this is because let me remember. This is because total variation distance can easily accumulate. If I remember, sorry, I suddenly cannot recall why why divergence-based definition is good for differential privacy. Roughly speaking, divergence-based is for example, Rini divergence. They are basically all lateral ratio based. Essentially, they're always based on the lateral ratio. So in differential privacy, the lateral ratio is important because this makes it easily to translate the Rini differential privacy to epsilon delta differential privacy.
I could understand because if you use Neumann-Pearson lemma, mostly you will check the ratio of density function. So that's you use this KR divergence or Rini divergence. Sure. Yeah.
Great. Are there more questions? If no more questions, let's all thank the speaker.
Thank you.
Thank you very much. And yeah, thank you everyone for coming. Yeah, 谢谢。
谢谢大家。
好好好，好好休息。